In 1855, Napoleon III of France hosted a grand banquet for his most important guests. His honored visitors ate with gold and silver cutlery, but Napoleon himself, the most powerful man in Europe, ate with something more precious than either: aluminum cutlery. At the time, aluminum was rarer than gold. A single kilogram cost more than a skilled worker earned in a month. Napoleon displayed it alongside the French crown jewels at the Paris World's Fair. It was the most exciting metal on the planet. Today, you throw it in the bin after a sandwich. Aluminum foil, drink cans, aircraft fuselages, laptops, car engines, window frames, bicycle frames, space telescopes. How did the most expensive metal in the world become the most disposable? And how exactly is it made? From a reddish rock dug out of the ground to the thin sheet wrapped around your leftovers? That is what we are here to find out. Aluminum is the most abundant metal in the Earth's crust. It makes up roughly 8% of the ground beneath your feet. It is literally everywhere, in rocks, in clay, in soil. And yet for most of human history, nobody could get it out. Unlike iron, aluminum never appears in its pure form in nature. It is always chemically bonded to other elements, locked inside minerals like bauxite, and breaking those bonds requires enormous amounts of energy. Early 19th century scientists knew it was there. They just couldn't reach it. The first tiny samples of pure aluminum were produced in 1825 by a Danish chemist named Hans Christian Ørsted. Yes, the same man who discovered electromagnetism, but the quantities were microscopic and the cost was astronomical. For the next 60 years, despite being the most common metal on Earth, aluminum remained rarer and more expensive than gold or platinum. That is why Napoleon used it as a status symbol. Then, in 1886, something extraordinary happened. Not once, but twice, simultaneously, on opposite sides of the Atlantic Ocean. A 22-year-old American student named Charles Martin Hall, working in a woodshed behind his family home in Ohio, discovered that he could dissolve aluminum oxide in a molten mineral called cryolite and then pass electricity through it to extract pure aluminum. On the exact same day, February 23, 1886, a French chemist named Hall-Héroult made the identical discovery in Paris, working completely independently. Hall and Héroult never collaborated. They never even met until 1911, but they had solved the same problem at the same moment. Remarkably, both men were born in 1863. Both died in 1914, both age 51. Their process, the Hall-Héroult process, is still the only commercial method used to make aluminum today. Over 130 years later, not a single viable alternative has been found. Step 1. Find the bauxite. Aluminum begins as bauxite, a reddish-brown rock found mostly in tropical and subtropical regions. Australia is the world's largest producer, followed by Guinea, China, and Brazil. The ore sits just below the surface, often only a few meters down, making it relatively easy to mine. Open-pit mining strips away the topsoil and scoops out the bauxite with enormous excavators. The ore contains between 30 and 60% aluminum oxide. The rest is iron oxide, silica, and titanium dioxide. All of it needs to come out before the aluminum is useful. The raw bauxite is crushed and transported to a refinery, where the real chemistry begins. To produce just 1 ton of aluminum, you need approximately 4 to 5 tons of bauxite. Step 2. The Bayer process, turning rock into white powder. The crushed bauxite is mixed with a hot, concentrated solution of caustic soda, sodium hydroxide, and pumped into giant high-pressure vessels called autoclaves, where the temperature reaches between 110 and 270 degrees Celsius. Under this heat and pressure, the aluminum oxide in the bauxite dissolves into the caustic soda, forming a solution called sodium aluminate. The impurities, iron oxide, silica, titanium, don't dissolve. They sink to the bottom as a thick red sludge, called red mud. The sodium aluminate solution is pumped into tall cooling tanks called precipitators. As it cools, tiny seed crystals of aluminum hydroxide are added, triggering the growth of solid crystals that settle at the bottom of the tank like sugar crystallizing from syrup. These crystals are collected, washed, and then roasted in a kiln at over 1,000 degrees Celsius, which drives off the water and leaves behind a fine white powder, alumina, aluminum oxide, pure white. Looks exactly like table salt. This is now halfway to aluminum, but the hardest part is still ahead. Step 3. The Hall-Héroult Process, where electricity creates metal. White alumina powder is fed into a large steel pot lined with carbon. Inside, a molten bath of cryolite, a rare fluoride mineral, has been heated to around 960 degrees Celsius. The cryolite dissolves the alumina, lowering the melting point enough to make the electrolysis practical. Large carbon electrodes, called anodes, are lowered into the bath from above. A massive direct electric current is passed through the system, and here is where the chemistry happens. The electricity breaks the chemical bond between aluminum and oxygen. Molten aluminum metal, denser than the surrounding liquid, sinks to the bottom of the pot and collects there like a pool of liquid mirror. The oxygen that is released reacts with the carbon anodes, producing carbon dioxide and slowly consuming the anodes, which have to be replaced regularly. Every few hours, the molten aluminum is siphoned out from the bottom of each pot using a vacuum system and transferred to a holding furnace. Now here's the scale that makes this staggering. A modern aluminum smelter contains hundreds of these pots, each running continuously, 24 hours a day. A single smelter consumes as much electricity as a small city. In fact, aluminum production accounts for roughly 3.5% of all electricity generated on Earth. That is why the world's largest smelters are built next to hydroelectric dams in Iceland, Norway, and Canada, wherever electricity is cheapest and most abundant. Step 4. Turn the liquid metal into something useful. Pure aluminum coming out of the smelter is actually quite soft and weak on its own. To give it the strength needed for real applications, alloying elements are added to the molten metal in the holding furnace. Copper, magnesium, manganese, silicon, or zinc, depending on what the aluminum will be used for. The alloyed metal is then cast into large solid blocks called ingots or billets, or fed directly into continuous casting machines that produce coils of aluminum sheet. These are then rolled, sometimes cold, sometimes hot, through a series of rollers that squeeze the aluminum thinner and thinner. Aircraft-grade aluminum sheet can be rolled down to just a few millimeters thick, then heat-treated to achieve the precise strength and flexibility specifications required. Aluminum foil, the kind in your kitchen, is rolled to just 0.006 millimeters, so thin it is partially transparent. So thin you could stack over 150 sheets and they would be thinner than a single human hair. 5 facts about aluminum that will change how you look at it forever. Fact 1. Recycling aluminum uses only 5% of the energy needed to make new aluminum from ore. Not 50%, not 20%, 5%. That is why aluminum recycling is one of the most economically important recycling processes in the world. Every aluminum can you recycle saves enough energy to run a television for 3 hours. Fact 2. The Washington Monument, the famous 555-foot obelisk in Washington, D.C., was topped with an aluminum cap in 1884. At the time, it was the largest single piece of cast aluminum ever made. They chose it because it was the most prestigious, impressive metal available. It is still there today. Fact 3. Iceland, a country of just 370,000 people with no bauxite deposits whatsoever, is one of the world's largest aluminum producers. The reason? Cheap geothermal and hydroelectric electricity. Iceland imports alumina powder, uses its abundant renewable energy to smelt it, and exports aluminum ingots. The entire country is basically one giant aluminum smelter powered by volcanoes. Fact 4. A Boeing 747 contains approximately 75,000 kilograms of aluminum, roughly 80% of its structural weight. Without aluminum, commercial aviation as we know it would not exist. Aluminum's combination of low weight and acceptable strength is the reason a 400-ton aircraft can fly at all. Fact 5. The Hall-Héroult process, invented in 1886 by two 22-year-olds, is still the only industrial process used to make aluminum today. Over 130 years of research by the world's most advanced material scientists, and nobody has found anything better. Napoleon's most prized possession, the cap on America's most famous monument, the skin of every commercial aircraft on Earth, the foil around your lunch. All of it starts as reddish rock in a tropical mine. passes through two extraordinary chemical processes, one invented in 1887, one in 1886, and emerges as the most versatile, lightweight, recyclable metal ever discovered. And the two men who unlocked it, born the same year, died the same year, discovered the same process, on the same day, on opposite sides of the world. You genuinely cannot make that up. Every week we open a new file, a new object, a new material, a new invention, and every single one has a story this good hiding inside it. Subscribe so you don't miss the next one. The Object Files. Every object has a case.